from this for calculus from our 1.2 section where we were looking at finding the derivatives using the definition. I will show you the longer way, the way that they are asking you to find it in 1.2, and I'll also look at a couple of problems related to the tangent line or tangent equation. Um, but I will want to show you as well the shortcut way that's specifically talked about in 1.3. So I'm going to be just kind of working through a few homework problems, again from 1.2, and just had a couple of questions about these problems, and I just thought I'd make a video, and that way everybody can, kind of access it. So I'm going to share my screen, and I'm going to go to my document camera to work through some problems here. Mm-hmm. Don't want to do that one. Sorry, give me just a second. Here we go. Okay. So what you see, and I hope that it's pretty clear, but what you see here is problem number 14 from 1.2. And it's asking us to, for the given function, f of x equals 2x squared, it's asking us to, for part A, find the slope of the secant line through the points 1 f at 1, and then 1 plus h, f at 1 plus h, okay? So, and then on part B, we'll find the slope at that particular first point, 1 f at 1, or 1 f of 1, and then for part C, we'll then write the equation of the tangent line at that first point, 1 f of 1. So the first thing we need to figure out or think about is the formula for slope for a secant line. And this is just basically, I'm going to put right here, like my pen is trying to go out already. And this is just basically the slope formula, the change in the y. So we all know that y is basically the function evaluated at x. So the change in the y, the second point here, minus the change in the x. I'm sorry, the change in the y on top over the change in the x on the bottom. So I'm going to just put the basic definition first, just f at a plus h. This is what you'll find in your notes, over a plus h minus a. Okay, so this again is the change in y over the change in the x. Okay, now for our particular points, which we have 1 f at 1, our first point, and 1 plus h, and then f at 1 plus h, we're going to edit this formula to be in alignment with our particular points. So we'd have f at 1 plus the h minus f at 1 over 1 plus h minus 1. Again, change in the y over the change in the x. I'm just editing this original formula to match up or be in alignment with our particular points. Okay, so remember, this is your first point. You can think of this as point number 1. So this is your x, this is your y, and this is considered point number 2, x2, y2. Okay, or x and y still. So the change in the y over the change in the x. Okay? So what we're going to do now is take our function and apply it. Okay? So where we have x, we're going to replace it with 1 plus h because this is f at 1 plus h. And again, our function right here, f of x, is 2x squared. So we would have, when we actually plug in our particular formula or function, we would have, it's originally 2x squared. We would have 2, 1 plus h squared, and then minus 2, 1 squared. So where we had x, we replaced it with 1 plus h, and we replaced it with 1 right here. Okay? Our function was 2x squared. Then on the bottom, we still have technically just 1 plus h minus 1, but if you drop off those parentheses, look at what happens to the ones. The ones cancel out. So this essentially is just over h, okay? Wherever we can simplify, of course we would. All right. Now, continuing on, I'm going to FOIL this out. We have to do some algebra. So this is 1 plus h squared, a binomial squared, so I need to FOIL this out. 2, and so 1 plus h times 1 plus h. And then I'm going to just kind of keep this as just minus 2 because 1 squared is just 1. So 2 times 1, that's just 2. So I'm just going to put that down as a minus 2. And then that's still over h. Okay? Continuing to clean this up. I'm going to FOIL. So I'm going to keep this 2 that's hanging out. And I'm going to FOIL this out. First times first, that's 1. The outer is 1h, and so is the inner 1h. So that's 2h. So I've got plus 2h. I'm foiling, so I combine the inner and outer terms. And then the last times the last, I get h squared. And then I still have that minus 2, and I still have over h. All right, now I'm going to distribute this 2, and that gives me 2 plus 4h plus 2h squared. And then now I'm going to bring down that minus 2, and then I have over h. Okay? All right. So right now, all we're doing is finding the slope of the secant line. Remember, a secant line is just a line that has 2 defined points on it, okay? So basically, we're just finding the slope between these 2 points. That's it, okay? Cleaning this all up, the 2's cancel here. So right now, I've got 4h plus 2h squared over h. So I'm going to be able to factor out an h here on top. That will then allow me to cancel that h on the bottom once I pull it out. So I'm going to factor out an h, and that leaves me with 4 plus 2h, and then I still have over h. So the h is now canceled, and I've got 4 plus 2h. That is my slope of the secant line. That's my answer for part A. Okay? Now, for part B, we scoot it down here. For part B, it says find the slope of the graph at this particular point, 1f at 1. So instead of us actually thinking about slope between 2 points, such as part A, now we're looking for, if you want to, you can think of it as instantaneous change, okay? Or in other words, we're going to take the limit, okay? So when we're talking about the slope of a graph at a particular point, that is basically just saying finding the tangent slope. Part B, essentially, is finding the tangent slope. When you're talking about the slope at a single point, that's the instantaneous slope, which is just the derivative. But it's also called the tangent slope. Now, to get the tangent slope, which is just the slope at a single point, it is defined, put that so that you'll have it, tangent slope, which is the derivative essentially, is defined as the limit of the secant slope, which is the slope from part A. So essentially, when we take what we did from part A and we then just take the limit of it, we've got instantaneous slope. We've got the derivative. We've got the slope at a single point. So for part B, we're going to find the limit as h approaches 0 of our particular equation from part A. F at 1 plus h minus f at 1 over just the h, essentially. I'm going to go ahead and put what it was originally, though, 1 plus h minus 1. Now, keep in mind, we already know this answer. And I'm sorry I smeared that. But keep in mind, we already found what this slope is for the secant line. Now we're just going to take the limit of it. So I'm just going to bring over limit as h approaches 0. And this right here is 4 plus 2h. So I'm going to take the limit as h approaches 0 of 4 plus 2h. So essentially, when h approaches 0, I can just think about this as direct substitution. Let h equal 0. Then I would get 4 plus 2 times 0, which is just 4. So the slope of the line, or the slope of the graph at the point 1f at 1 is just 4. Okay? So slope at 1f at 1 is 4. Okay? And that's important. So think about this now. We just found the slope at this particular point. All right? Now I'm probably going to need some paper here for part C now. So I'm going to kind of move this on up a bit. I tell you what, I will take off these other pages, these other problems I'm going to look at in a minute. All right, so think about what we just did. We just found the slope at a single point. All right, now on part C, which is the tangent slope, okay? Now on part C, it says find the equation of the actual tangent line at the point 1f at 1. All right, so for part C, okay, so for part C, we want to write the equation of the tangent line at 1f at 1. Okay, given also that we have slope, or that we found slope, tangent slope actually. That's important. We want to use the part B because we're talking about the tangent line. We found the tangent slope from part B. So think about what we know. Think about algebra. We've got a point, or we will have that point in just a second, and we've got the slope. So we're going to use point slope formula to write the equation, which is the change. Well, let me not say change. It's y minus y1 equals m parentheses x minus x1. And this is, of course, where we have a point, given a point that we're going to substitute in for x1, y1, and given slope. Okay? So our point right now, we know the x coordinate of it. We know that it's 1. Okay? So this is the x coordinate. This is our x1. All right. Now, what we're going to do now is make sure that we have f at 1. So we're going to complete the point, basically. So we've got the point 1, f at 1, that we'll plug in here along with the slope that we found from part B. And so my formula, my equation rather, was what was it? F of x equals 2x squared, okay? So if I let x be 1, then to complete this point, I would have 2 times 1 squared, which we kind of already know. I believe we saw it right here in part of the formula. But anyway, we'll work it out again. So we're plugging in 1 for x, and that gives us 2 times 1 squared, which is just 2. So our ordered pair that we're going to use for x1, y1 is the point 1, 2. Okay, all I did was plug in 1 right there. 2 times 1 squared gave me 2. And then our slope, our tangent slope from part B is 4. So we've got y minus 2 equals 4 parentheses x minus 1. Now, they may accept it in this form, but they also may, it depends on the question, they may ask you to go ahead and clean it up, simplify it, and put it in y equals mx plus b form. And that's just where you get the y by itself, all right? So doing that, I would need to get rid of the parentheses. So I have y minus 2 equals 4x minus 4. And then I'm going to say plus 2 to both sides. So y equals 4x minus 2. And there's my equation. There's my part C. Okay? So it really is just a matter of you using that definition or that formula, and it could get, I guess, a little, not necessarily hard, but just lengthy in evaluating or simplifying through the formula, depending upon what the original function was. This function actually wasn't that bad, so that problem wasn't terrible. Okay? Let's look at another one here. I want to look at number 15 as well. Okay. And I'll answer any more questions that you have. I'll answer those in class, but I just wanted you to have this video to just kind of be able to look at this a little bit more in detail, even before we see each other in class on Thursday. All right, so let's look at number 15 here. So this one says for f of x equals 1 over 7 plus x squared, the slope of the graph of y equals f of x, so the slope of this function, the slope of f of x, is said to be negative 1 over 32 at a single point or at a particular point with the x coordinate of 1. So basically the instantaneous slope or the tangent slope at 1, at x equals 1, is negative 1 over 32. And we want to find the equation of the tangent line at that point. So this is essentially basically like the part C from number 14. It's just kind of giving us a little bit extra that we didn't get in number 14. Number 14 was a bit more involved. They actually give us the slope here. So given tangent slope, which is negative 1 over 32 at x equals 1, complete the ordered pair. So we've got the x coordinate. We're going to figure out what the y is, and we plug in x. Complete the ordered pair and write the equation. That is what we're going to do. Okay? So we're going to, of course, use point slope form because that's what we have. We have the slope, and we're going to have a point in just a second. Use point slope form. Now, I know on this problem, they will accept you to leave it in point slope form, which is y minus y1 equals m parentheses x minus x1. Okay, so right now we've got m, which is negative 1 over 32. We need our x1, y1 point. So slope, tangent slope is negative 1 over 32 at x equals 1. So we've got the 1 coordinate. Let's evaluate, we've got the x coordinate, I should say. Let's evaluate the function at 1 to get the y coordinate. Okay, so f at 1 would be 1 over 7 plus 1 squared. All I did was replace the x with 1, okay, to get the y coordinate. Because remember, x is the independent and y is the function evaluated at the x, or it's the y coordinate, okay? So this becomes 1 over 8, because it's just 7 plus 1. So that becomes 1 over 8. So we have y minus, so this ordered pair is now 1 over 8. So we have x1, y1. So we have y minus 1 over 8 equals negative 1 over 32 parentheses x minus 1. And remember, when you're writing your equation, your x and y stay because it's an equation um, based on x and y. Okay, we just replace the x1, y1, make those constant values. And then we can leave it in this form. I did check the solutions and they will accept that form. But if you did want to clean it up, then you would use the distributive property and you would have y minus 1 over 8 equals negative 1 over 32x plus 1 over 32. Okay. And that's just where I had a negative times a negative. That's how that became plus. And then I would take that negative 1 over 8 over here to 1 over 32, because if I'm putting it in slope-intercept form, then this is supposed to be y equals. It's supposed to have y by itself over here. So I would say plus 1 over 8. It cancels there, and I have y equals negative 1 over 32x. And then, of course, you do not have to find common denominators and all that by hand. Whip that in your good calculator here. Add 1 over 32. I'm just going to use these parentheses here, plus 1 over 8. When I'm dealing with fractions, I like to see the fractions, so I kind of separate them, but making sure that I do understand that it's plus, okay? So I do have a plus in between. Now, when I press enter, of course, it gives me a decimal. If you press the math key under alpha here, then it will allow you to choose to change it to a fraction. So I'm going to choose to do that. Number one is highlighted. I'm going to select it by pressing enter and then select it again to actually transform the answer to a fraction. And that becomes 5 over 32. And it's positive, so I would say plus 5 over 32. So you can either leave it in this original form, which I'll circle here. This is point slope. If they do want it in y-intercept form or slope-intercept form, it would be here in this form. Okay, and that's because, again, you got the slope and you got the y-intercept or point slope. Okay, that's number 15. And I'm not working every problem. Number 16 is very similar to 15, if I'm not mistaken. Or better yet, I believe number 16 is like number 17. But number 16 was way easy. So I figured I would do 17 and 18, and then you should be able to do 16. So the next problem I'm going to work is actually related to using the four-step process to find the derivative. Okay. Now, keep in mind, in 1.3, we talk about the differentiation formulas. So we alleviate the need for the application of the long definition of the derivative. You know, the long definition involves taking the limit, okay? It involves taking the limit of the secant line. So basically the change in the y over the change in the x and then taking the limit as h approaches 0. But once you get to 1.3, you have these shortcut formulas that just make finding the derivative that much more easy. So I will show you the definition and then I want to show you the shortcut too. I just kind of want you to see both. Because again, once you get to 1.3, you'll no longer use the definition. You'll use the formulas. So let's look at number 17 here. Find it. I think I copied it. Here we go. Okay, so here it says use the four-step process, which again is the definition of the derivative using the limit. So I'm going to put that down, definition of derivative. That's what that four-step process is talking about. So that is, and we're calling our function s of x. So to get the derivative, we're calling it s prime. So I'm going to call it that when I actually write it out in the definition format. So to get the derivative of s, I take the limit as h approaches 0 of the change in the y. So s at x plus h minus s at x over h. Okay? Remember that denominator? It essentially ends up just being where the x's cancel out because it's x plus h minus x. So it just essentially becomes just h. Okay, and then we're going to be taking the limit. All right, so that's the definition of the derivative. So what we're going to do is take our original function and we will evaluate it at x plus h. Okay, right here in that first part, and then minus the original right there, all over h. So I'm going to show that right here, the limit as h approaches 0. This would be 2x minus 5, so it's going to be 2x plus h minus 5. And then I have minus the original. So minus, and I am putting parentheses here because this has two terms. So I want to make sure we understand that we're subtracting the whole thing. So minus 2x minus 5. And then all over the h. Okay? Cleaning this up, continuing to go through it. So I'm going to use the distributive property to get rid of the parentheses there. And I will even use the distributive property here to distribute that negative sign. Okay? So I've got 2x plus 2h, and then I've got this minus 5 that's just kind of hanging out. It's not affected by the 2. And then right here, this is going to come down as a plus 2x and a plus 5. And then I have over h. Okay? Continuing to clean this up on the top. Oh, I'm sorry. I did not bring down that minus on that one. That is minus. Okay? It was positive in there, but then I'm taking the minus through. Okay? And then that was minus, but it took the minus through and it became plus. Okay, so be careful with your signs. All right, so now what's going to happen is the 2x and the minus 2x cancel. The minus 5 and the plus 5 cancel. So I've got the limit as h approaches 0 of 2h, okay, 2h is all I have on top, over h. Well, I've got the limit as h approaches 0. The h's, they cancel out. So I essentially have the limit as h approaches 0 of 2. So the limit as h approaches 0 of a constant is just that constant. There's no h there, so it's just 2. And because the derivative, because this is the derivative, this is s prime of x, because the derivative is just a constant function, then that means every one of these answers here, where we evaluate the derivative at each of these values, is still just that constant. So let me put that. Because the derivative is a constant, remember constant just when it's just no variable, just a number. Because it's a constant function, then all three, s prime at 1, s prime at 2, and s prime at 3, all three of these are just equal to 2. Okay? Let me show you how we would, if we were given this same original function here, if we were given that same original function in 1.3, how we would find the derivative. So let's say we apply the formula here. This is the answer, though. You would actually plug in right here 2 and then 2 for each of these as well. Okay, the derivative was a constant. So when you're dealing with a constant function, no matter what x you plug in or where you evaluate it at, it's still that constant function answer. Okay. Now let's suppose that you were given this same formula or this same function, I should say, the same function in 1.3. Okay. And let's say you were told to find s prime. Now, according to the power rule for derivatives in 1.3, you have to consider that this has an exponent of 1 here, okay? So to get the derivative, we would subtract, we would bring down the old exponent. Let me say that. The exponent is 1. We would bring down the old exponent, and there's already a constant there in front of it, so I would be multiplying that old exponent, because this is 2x to the first minus 5. I would be bringing down that 1, multiplying it to that coefficient that's already there, and then I would reduce the exponent by 1, okay, for that first term. Now, for the second term, this is a rule that we'll see in 1.3 that you've probably already seen. We may have mentioned it a little bit. We didn't get into 1.3 that heavy, but we'll talk about it more on Thursday. But when we actually when we take the derivative of this constant here that's subtracted there, that constant, the derivative of a constant is always just zero. So it essentially just drops off. So the derivative final answer here ends up being 2 times 1, that's just 2, and this is x to the 0. Well, x to the 0 is just 1, okay? Anything raised to the 0 power is just 1. So that essentially is just 2, which is what we got here when we worked through the definition of the limit, when we applied the definition of the derivative using limits. Got the same answer. Okay? Let's do another one of those. This is number 17. Let's do one that's a little bit more involved. I'll look at number 18. So it says use the four-step process. Again, that's just the definition of the derivative. This time our function is a polynomial, x squared plus 7x minus 7. So definition of the derivative means we take the limit of the secant line, basically. So the limit as h approaches 0 of s at x plus h minus s at x all over h. So that means I'm going to take this function, this original function, and where I see x, I'm going to replace it, this first part, I'm going to replace it with x plus h, okay? So this becomes, let's see here, this becomes x plus h squared plus 7 times x plus h. Wherever I see x, I'm replacing with x plus h. And then I have minus 7. So that's this first part. Then I have minus the original f of x. And I changed it to s, and I shouldn't have. Thinking about that previous problem there, I am so sorry. That is f of x. So the derivative is called f prime, okay? And then I have minus the original function, x squared plus 7x minus 7. And that is all over h, okay? So I am going to basically just kind of start cleaning this all up a bit here. We've got, let's see here. We've got to FOIL this out. So I've got the limit as h approaches 0. I've got x plus h times x plus h. Then I've got, and I tell you what, I'll go ahead and simplify that by using a distributive property. So then I've got plus 7x plus 7h, and then I still have that minus 7. And I think I'm going to go ahead and distribute this minus here through as well. That means these signs are going to change when they come down. So that's going to come down as a minus x squared, a minus 7x, and then a plus 7. And that is now all over h. Now I'm not done because this right here has to be FOILed out. Okay, everything else has kind of been simplified. And this is going to clean up really nicely. It's just a little bit of algebra initially in the beginning. And remember at the end, once we've simplified it, cleaned it up, then we'll take the limit. All right, so right now I've got FOIL. So I've got x times x, that's x squared. Okay, my outer is hx. And my outer is hx and my inner is hx. So I've got a plus 2hx. And then my last times my last is h squared. So plus h squared. And then everything else, I just rewrite. All over, ooh, pen, all over h. Okay, so let's see what cancels here. The x squared cancels with the x squared. The 7x cancels with the 7x. The minus 7 with the plus 7. Let's see what else we have here. Anything else? I think that's it. That will cancel. So I now have limit as h approaches 0 of 2hx plus h squared plus 7h all over h. Okay? Now you can see how this is more involved than that previous problem because the original equation was a bit more complex. Not terrible, but more to do than that linear function was. Okay? So now, each of my terms on top all have an h. I'm going to factor out that h. So I'm going to take the limit in a minute, but right now I'm just kind of letting it hang out. And I'm going to factor out that h, and that leaves me with 2x plus h for that middle term because I had two of them and I pulled one out, and then plus 7. And then here on bottom, I still have h. So the h's cancel. I've got limit as h approaches 0 of just 2x plus h plus 7. Okay? Now, to actually evaluate the limit, let h be 0. So that essentially is just 0 right there. So we got 2x plus 7. 2x plus 7. That's our derivative. So f prime of x is 2x plus 7. Okay? Now we'll take that and we'll evaluate the function. We'll evaluate the derivative at 1, at 2, and at 3. So f prime at 1 would be 2 times 1 plus 7, which is just 9. Just 9. I don't know why I paused. All right. All right, so that's just 9 there. And then f prime at 2, 2 times 2 plus 7, that is 11. And then f prime at 3, 2 times 3 plus 7. So that's 6 plus 7, that is 13. Okay, so yeah, those are our answers. Not too bad, really. Now, let me show you the shortcut. Now, if you were seeing the same problem in 1.3, you would not have had to do all of this, okay? So let me show you this. Think about it using derivative formula. And I actually don't blame you if you just use the derivative formula even in 1.2, because even though it says use the four-step process, after this section, you won't even bother with it. So who's going to know that you even used or didn't use the longer process here in this? You can use the shortcut. You can use the derivative formulas. So if I use the derivative formula, which is basically going to be the power rule in this case, f of x, the original function, was x squared plus 7x minus 7. So I'm going to find f prime, okay? Now that would be where I take the old exponent, I bring it down, and I reduce that exponent by 1. So that first term would come or become 2x. 2 comes down, and then the old exponent gets subtracted by 1. So 2x now, with the understood exponent of 1. Here, this term just becomes 7 because that has an exponent of 1. It gets brought down. And then that now has an exponent of 0. And x to the 0 power is just 1. So that's just 7. That's just plus 7. And then the derivative of a constant just drops off. It's just 0. So there it is right there, 2x plus 7. And all I did was apply the power rule from 1.3 for derivatives. And again, look at that in 1.3. Section 1.3. There is no issue with you using the shortcut, using the formula if you so choose, even in 1.2. It would not be a problem, okay? All right. I think that's all I have really for today. I just wanted to show you a few problems. Oh, let me show you on number 20 why I definitely recommend using the derivative formula. Um, I'm not going to necessarily work it out in this video. I'll work it out in class on Thursday if you want me to, the long, long way. But you'll see why I recommend using the formula, especially when you're dealing with equations that are a bit more involved. Like take a look at this one. You're dealing with the square root. So you can imagine applying the definition of derivatives or the actual definition of derivatives involving the limits. It would take you um, taking this original formula or this original function and replacing x with x plus h. So you have a square root. You have to somehow figure out how to simplify that, clean that up. It could get kind of nasty. Okay. I'm gonna just kind of set it up so you can see what I mean here. So if I was actually applying the definition, I'm just gonna kind of introduce it. It's a bit lengthy. The limit, and my video is kind of running long, but I'll work it out if you want in class. But I do recommend that you take a look at those formulas in 1.3, which we will in class. So here is the definition of the derivative using the limit, okay, using limits. So essentially, I would literally have to take that function and replace the x with x plus h. So this is how it would end up looking. Let me show you. So let's call that f prime, because that's what it is, a derivative, as h approaches 0. So this would be 10 square root, okay, where I have x, I now have x plus h, and then I've got plus 1. Okay, then I've got minus the original, so just 10 square root x plus 1. And then I have all over h. So you might be looking at this like, what can I do to this? Because these do not match. So I can't bring them together. I would literally have to introduce conjugates. It's where I would multiply top and bottom by the conjugate of this numerator. And it can get nasty. This is what the conjugate would be. 10 square root, basically just the opposite sign here. These two terms would be the exact same, but this will become a plus when I multiply. So 10 square root x plus h plus 1 plus 10 square root of just x plus 1. And the conjugate, multiplying the top by that, we have to do the bottom by that as well. So it's like the numerator might clean up, but then I have it on the bottom now. So it still will eventually, kind of work out, but it's going to take a little bit of time. Okay. So this is what you would this is where you would kind of start with that part. Okay. I'd love for you to try a little bit on this one. And like I said, I'll finish it up. But um, yeah, I recommend that you look at the formulas. But let me kind of show you what happens here when you multiply this top by its conjugate. Yeah, let me go ahead and kind of show you a little bit more. So we've got the limit as h approaches 0. So when you multiply 10 radical x plus h plus 1 times 10, basically by itself, the 10 and the 10 become 100. These two expressions are now just going to not have the radical anymore, because basically it's like square root of x plus h plus 1 squared. So the square root and the square cancel out, and it's just x plus h plus 1. Okay, think about it like this. If you had square root of 2 times square root of 2, this would be square root of 2 squared. Okay, so the square and the square root would essentially just cancel and just leave it with 2. So that's what's happening here. The square roots are just canceling, and I'm just left with what's underneath, the x plus 1. And the same thing is going to happen um, to this second term here. It's plus times a negative, so it is going to come down as a negative or minus. 10 times 10, that's 100. And then the square root of x plus 1 times the square root of x plus 1 is just x plus 1. All right, and then on the bottom, I end up with h times all of that. 10 square root x plus h plus 1 plus 10 square root x plus 1. Okay, and so you would literally just have to kind of keep simplifying, use a distributive property. It actually is looking a lot nicer already, believe it or not. But you just have to keep cleaning it up. Use the distributive property here, multiplied through by 100, and then here by that minus 100. Kind of let the bottom hang out for a minute. What I would do though is pull out that 10. So let's see. On top, I have 100x plus 100h plus 100. And then I've got minus 100x minus 100. And then on the bottom, I have 10h. I'm going to factor out that 10. I'm going to put it out here with the h. And then I have inside these parentheses, square root of x plus h plus 1, and then plus square root of x plus 1. Okay? So try to see if you can work with this. See what you can do with this. And I will pick back up here, but I'm going to stop the video for tonight. And I'll pick back up here. I'll finish it out if you're struggling. But see what your algebra skills will kind of allow you to come up with. Let me know what you get. And I'll see you in class.